right, if you would go and take your homework out and turn in your textbooks to page 281. Page 281. We've been working on reducing radicals, making the radicand smaller. You just said I'm on the back row there, thank you. Making the radicand smaller, and the basic premise there is factor up the radicand, factor up the number into at least one factor that you can take the root of. And with letters, of course, we said we just see how many times does the index go into the exponent, dividing exponent by index. You had page 281, numbers 21 to 29, the odd, and page 284, numbers 9 to 12. 29 through 31 odd. That's a 21 to 29 odd. Yeah, that wasn't what I said at all, was it? No, you didn't. You did 21 to 29 odd and 9 to 12. She did 29 to 31 odd. I figured she would shorten the homework a lot that way. I'm sure it wasn't on purpose. Okay, so let's go and take a look at these together. Starting with number 21, where we have the square root of 12x cubed. And again, as we look to make the radicand smaller, Noah, we want to start by factoring the 12. You can't take the square root of 12, but there's a part of 12 or a factor of 12 you can take the square root of. 4. So we're going to factor into 4 times. But again, don't lose the letter. Go ahead and keep the letter for now. Once you've factored the number, you go ahead and take the root of the number you can take the root of. Well, the square root of 4 gives you a 2, and then you leave the part you can't do nothing with. 3. The 3. Once the number is taken care of, then we deal with the letter. And remember, with the letter, we're not factoring it up. We're simply asking how many times can this go into that. We are dividing exponent by index. And how many times does 2 go into 3, Noah? Once. So we pull out an x with how many left over? So we leave an x inside. And that's what we should have had for number 21. Did you have that? Did you have that also? Question on that. All right, no, she didn't have it. All right, number 23, we had 2 times the 5th root of 64, q to the 12th, r to the 16th. Now, Bracken, this is a 5th root. I don't have a big list of 5th roots that I've memorized, right? In fact, there's only one 5th root we have memorized. Maddie, help him? 2 to the 5th is 32. So we've memorized the 5th root of 32, but that's the only one we know, right? So, well, I don't know. Is there a 32 in 64? There is. So it's a good thing that we know the 5th root of 32 is 2. If that didn't work, though, we would have had to figure out, well, what's 3 to the 5th? Maybe what's 4 to the 5th? Maybe what's 5 to the 5th, right? We just figure it out as we go, but this works out pretty nicely. So we'll factor that 64 bracket into. And again, for now, keep the letters. Then we're going to go ahead and take the 5th root of the to get 2. Now that gives me a 2, but I already had a 2 out here. So I get a 2 from the 32, plus times I already had a 2 out here. So now what's my coefficient number? 4. But inside the radical, I still need to leave the number 2 from this one right here. So we're going to leave the 5th root of that 2. Now we're ready to go to the letters. And remember, for the letters, we divide the by the. In other words, we ask how many times does this go into that? How many times does this go into that? 2 times with 2 left over. How many times does this go into that? With, and there's our answer, and that's all there is to it. Did anyone get this answer for number 23? All right, good. Let's take a look at number 25, where we have the square root of 25 x squared y cubed. Bracken, I'm going to stay with you because this one's a little bit unique. The square root of 25. I couldn't take the square root of 12, so I had to factor it. I couldn't take the 5th through to 64, so I had to factor it. Thoughts on the square root of 25? It's just 5. I don't need to factor it. I can just take the square root and get a 5. No number needs to be left inside the radical because it came out evenly. So now we're ready to move on to the letters bracket, where I ask myself, answer? With no x's even left inside the radical. Okay, continue. So the only thing that's going to be left in the radical is the y. How many had 5xy times the square root of y for number 25? Good. All right, let's take a look at number 27, where we had the square root of 500 xy cubed. Now, Noah, you cannot take the square root of 500. So unlike Brecken's problem a moment ago, where we had the square root of 25, hey, that's rational. That comes out even. Not rational. Doesn't come out evenly. So what do we need to do? Split it up. Factor it, right? How might we factor a 500? You could do 25 times 20, but there's a way better square than 25 for 500. Anyone? How about 100? Right? Anytime it ends in double zero, use the fact that 100 is a perfect square. Now, Noah, to be fair, if you said 25 times 20, you could then further factor this to get 4 times 5, and really what you have is 100 times 5 anyway. So you could have still gotten down to this point, but I'm lazy. I don't want to do all that work. So just note, double zero ending, use the 100 that's in 500, right? So that would have given us, oh, and don't forget the letters, okay? So take it from here, Noah. All right, good. So now the number's taken care of. Now let's go to the letters.
Leave the x. And then bring one y, and then put one y.
There we go. 2 goes into 1, not at all, so leave it in there. 2 goes into 3 ones with 1 left. And there's our answer for number 27. Now, Noah, did you end up with this anyway? You did not. You ended up with 5y times the square root of 20xy. So again, you would have needed to go one more level down to get 4 times 5. Pull the 2 from the 4. That's where you would have gotten the 10y. And that would have left you with the 5xy. All right, questions on that? Anyone get that answer? All right. Number 29. Now, Maddie did do this one. So, Maddie, we're going to go to you on this one here. We had the cube root of 54 x squared y to the 6th z to the 5th. And, Maddie, how did you factor the 54? Good. So we're going to split that up 27 times 2. Of course, we still have the x squared, the y to the 6th, the z to the 5th. And continue. And by the way, easy mistake to make would be to forget the cube root part of this, right? To forget to copy the index. Don't forget to copy the index down. Okay, pray continue. There we go, 3y squared z times the cube root of 2x squared z squared. Did we get this answer for number 31? Questions on 31? Did we accidentally factor it 9 times 6 perhaps, Bracken? How did you factor it?
You missed the cube root, I did the square root.
All right, so if it were a square root, it should have been 9 times 6. If it had been a square root. You don't know how you factored it? You can't look at your work and tell me what 2 numbers you rewrote 54 as? That's a problem. That means our work's not very thorough, is it? All right, Noah, question, comment?
I got that, except I didn't put the little 3.
Ah, you forgot the index. Easy mistake to make. So didn't mean to be pegging you there when I said it'd be an easy mistake to make, but apparently I got you. All right, turn over to page 284 now. Let's take a look at numbers 9 through 12 there in the review section. This is wrapping up the first method of reducing radicals. If you look over at the bulletin board, you'll notice that there are 3 different ways to reduce radicals. Well, we are just about done with the first way, which means we still have 2 more to cover, which we'll get to in just a moment. First, let's take a look at 9 to 12 at the very bottom of page 284. And number 9 is, as far as the number is concerned, is a rather unsatisfactory problem because, Noah, how would I factor this 3? You don't. It's prime. You can't factor it. And I can't take the square root of it, so I just don't worry about the number. It's all about the letters here. What do we get for our answer?
2x times the square root of 3xy.
There we go. 2 goes into 3 one time with 1 left. 2 goes into 5 2 times with 1 left. Don't even worry about the 3. There's our answer. Did we get that for number 9? All right, Brecken, on the next one, we have the square root of 216 x cubed y to the 5th z squared. Now on the surface, Brecken, that number 216 is just a huge number, right? And so it can be a little bit daunting. But as you look at it, you should think, wait, 216 is a special number. What is 216? That's 256. It is something special. This is why we have to have these memorized, Maddie. This is 6 cubed, which means 6 times 6 times 6, which means 36 times 6. Now, you could have gotten there by dividing it by 2, divided by 3, divided by 5, divided by 6. Hey, there's a square, right? You could have gotten to that point, but a quicker way to get to this point would be to think, well, what is 6? What is 216? 6 cubed means there's 2 6s or a 36 or a square in here. So this would have been the ideal way to factor this. How many did notice the 36 in the 216 because it is 6 cubed? Does it make sense how we could have, should have seen that? Does it make sense now? All right. You could do the same thing with, say, if you had like the square root of 343. What square must be in 343? 7 squared, or 49, right? This has got to be 49 times 7 because that's 7 cubed, or 7 times 7 times 7, right? So sometimes you can cheat the system a little bit through memorized cubes every now and then. Continue from here now, Brecken. What should we do? And that should have been our answer there. Now, there are other ways you could have factored it. There is a 4 in there. There is a 9 in there. There's other ways to split it up. But this should have been our final answer. How many got this answer for this problem? Questions on this? Again, 9 times 24. Anyone go 9 times 24 in the factoring? So you had 3xy squared z times the square root of 24xy, Maddie? So again, do you see in the 24, though, there's still a 4. 4 times 6, so continue factoring down. Noah, did you factor 4 times something? 4 times 54?
Well, I did 9 times 12 instead of 24 for some reason.
Oh, okay, yeah, it should have been 9 times 24. Okay, gotcha. All right, let's take a look at the next one, number 11, where we have 5 times the cube root of 16, x to the 4th, y to the 5th. Maddie, thoughts? I'm sorry? Now I'm going to show you a shortcut that I use because I'm lazy, okay? I generally don't like rewriting the whole Radicand again. So what I'll often do is I'll just simply show the 2 factors, kind of scribble out the 16 here rather than having to rewrite the letters. Continue. Notice what I'll do here. Again, instead of rewriting the whole thing, okay, I'll simply scribble out the 8 and put the cube root outside here with the 5 so that I end up with Well, I'm not ready for the letters yet. There we go, 10 times the cube root of 2. Now we'll move to the letters, Maddie. Do you see how I do a minimum of writing this way? So again, the lazy way to write it, again, this isn't a great way to teach it because students are like, what did he just do? But we've done enough of these, I feel we're ready for this now. Is just factor up, scribble it out so you know it's not there anymore. When you take the root, again, don't write the 8 out here, write the cube root of the 8 out here, and then scribble the 8 out. So there's my 10, there's the 2, and then we can take care of the letters from there. And then we get this answer for number 11. This answer for 11, good. All right, and then number 12, we had the cube root of 27, x to the 4th, y to the 6th, z squared. Bracken, thoughts?
3.
Good, the cube root of 27 is 3. I don't need to factor this. That just becomes 3. Once again, there's no number left inside. Continue.
3 goes into 4 one time, 1 left over. It goes into the 6 2 times. Then 9 to the z squared on the side.
And there we go. And we get this answer for number 12. All right, Noah, good questions. All right. One more thing I want to show you. This is a little bit more Algebra 2 level, but I do want to show this to you. Write this down in your notes if you would. The cube root of x to the 5th minus x to the 4th y. We've been looking at monomials, right? Monomial, 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 roots of monomials. Here we've got the root of a polynomial. What in the world do we do with the root of a polynomial? Well, just like the number, with a polynomial, the key is factoring. Because you can take the root of a factor. Technically, that's even what we're doing, you might recall, with the letters. That's what I showed initially with the letters before saying, yeah, but there's an easier way. With this, the key is I can't take the root of anything until I see factors before me. And there aren't any factors here, are there? Not written. How could I factor the radicand here, Noah? No. You're trying to take the root. We're not ready for the root. You have to factor first. So ignore the radical. How would I factor that? Think back to our section on factoring. Good, there's a common factor of x to the 4th, which when I pull it out leaves me with x negative y. Now that we can see factors, now we're ready to approach the problem from the perspective of taking the root. How many times does this go into that? And so forth. So class, how many times does 3 go into 4? 1 time. So 1x is going to come out here. How many left over, class? 1. A single x left over. How many times does 3 go into 1, class? It doesn't. So no x minus y's come out. We will leave the x minus y inside. Does that make sense? Write this down. The square root of 18x minus 9. Maddie, the key to working with polynomials in the radicand is you have to factor. How would I factor an 18x negative 9? To get? Right, 9 times 2x minus 1. Now notice there are 2 factors. There's a 9 and there's a 2x minus 1. And you can take the square root of one of those 2 things, Maddie. The 9. The square root of 9 is 3. Can I take the square root of 2x minus 1? So I'm going to leave the square root of 2x minus 1. And I've reduced that radical as well. Consider this for just a moment. The square root of 3x squared, positive 6x, positive 3. Bracken, how would I factor this polynomial? To get?
X squared, positive 4x,
But think for just a minute, that should look really familiar, Bracken. X squared plus 2x plus 1. Perfect square, positive, even. That's a perfect square trinomial. It's been a little while, hasn't it? Do you remember how we would factor a perfect square trinomial? Well, we could backwards FOIL, but normally we said we would factor it into a binomial squared. Remember? We take the square root of the first, square root of the last, and the sign of the middle. Been a little while since we've done that. Y'all remember doing this now? And can I take the square root of 3, class? No. Could I take the square root of x plus 1 squared? Yes, because 2 goes into 2 one time. So 1, x plus 1 comes out with none left over. So this is how you would handle polynomials. You're not going to see this until next year in Algebra 2, but I wanted to kind of show a preview of what we will be doing a little bit next year with this. So when it comes to roots of factors, it's not just monomials that factor, it's not just numbers that factor, polynomials can factor as well, and we can work with those roots also. Questions on this? Questions on this? All right. Next section in your notes. Reducing radicals, part 2. Reducing radicals, Roman numeral 2. So we got Roman numeral 1, and we spent, now it feels like forever because we've missed a couple of days. Gavin, I don't know if you've noticed that the videos haven't been being uploaded particularly regularly. I was out sick a day, and then yesterday we were setting up for the academic fair. So for us, it feels like forever. May feel like forever for you, I don't know, but we're moving on now. Roman numeral 2, as we reduce radicals. Reduce means to make smaller, to make simpler, to make easier, right? You know something that isn't very simple or easy? Fractions, right? With that thought in mind, you can't have a fraction in a radical. It's not allowed. Can't do it. No fractions allowed in radicals. Well, question for you. What part of a fraction makes a fraction a fraction? Not the line. The denominator. Is this a fraction? No. Not until I put it over 1, right? And if there's no denominator, I don't need the line, right? In fact, even with the line, it's still not technically a fraction, so you put a denominator down there. So when we say, class, that if we don't want fractions, what we really don't want are denominators, right? The denominator is public enemy, number 1, when it comes to radicals. So what we have to do is eliminate the denominator from our radical. But you can't just cross it out, right? The proper way to get rid of the radical, the denominator from the radical, is to take the root of the denominator. So method number 2 in reducing radicals is to take the root of the denominator. This is referred to as rationalizing the denominator. Rationalizing the denominator, to make rational, right? When someone is rationalizing their behavior, for instance, Noah's like, you know, I know I shoved Brecken over the staircase, but I had a good reason, Mr. Nadasky. All right, try to rationalize your reckless, careless, destructive behavior. Poor Brecken. Well, I saw his face and I didn't like it, so I had to throw him over the staircase. Oh, okay, that makes sense. You know, as long as we can make it rational, right? Okay, just kidding. But rationalizing the number means to make it rational, meaning there's not a radical there anymore. Write this example down, if you would. The square root of 9/16. Now, we've seen problems like this already. I told you before, when you have the root of a fraction, take the root of the numerator and take the root of the denominator. So the square root of 9/16, Brecken, would give us 3 over 4. Do you notice, class, that I no longer have a denominator in the radical? The denominator is still there, but it's not in a radical anymore. Do you see that? I've rationalized the denominator. Seem pretty easy? Look, write this example down. The square root of 3/25. Now, we hadn't seen one quite like this before. And your initial thought as soon as you were writing it, Noah? You can't take the square root of 3, can you? But you know what? I don't care. All I care about is the denominator, right? And I can take the square root of the denominator. So what is the square root of 25? 5. No problem. What's the square root of 3? I don't know. The square root of 3. Notice there is still a denominator, but it's no longer in the radical. Do you see that? It's below the radical. It's not in the radical, it's outside the radical. You could also write this 1/5 times the square root of 3. Now, I don't prefer that method, but it means the same thing, right? Just like 1/2 x and x over 2 are the same thing. The square root of 3 over 5, 1/5 times the square root of 3, they're the same thing. I'm typically going to leave it this way, but notice the radical is only over the 3, not the 5 anymore. Does that make sense? So I still rationalize the denominator. Write this example down. The square root of 1/3. Here we have the reverse problem. We can take the square root of the numerator just fine, right? What's the square root of 1, class? 1. What's the square root of 3? Oh. You see, you can't take the root of the denominator, can you? But you have to take the root of the denominator. But you can't take the root of the denominator. You see the little conundrum? I'm going to use a silly illustration here, but how many of y'all put puzzles together, maybe with your family, sometime maybe over vacation, dump out, the 1,000-piece puzzle on the table that you're like, why are we even doing this? And like spread all these pieces and you're like, I don't know how we're going to do this. And you start putting the puzzle together. Anyone ever done a puzzle? You've done a puzzle. You've done a puzzle? Okay. You have done a puzzle. Okay. Now, every puzzle known to mankind, for some reason, a sadist takes the photograph that goes onto the puzzle, and there's always like this huge expanse of sky where every piece looks the same. Y'all know what I'm talking about? Okay? Or there's a large portion of like grove of trees or something where every piece looks the same. Or it's grass, or water, right? It's either water, grass, sky, or trees. But there's a bunch of pieces that look the exact same. I have seen this one puzzle. Now, it's a gag gift, but the whole puzzle is nothing but one tone of blue sky with a small crescent moon on it. That's the whole puzzle. And now, the best part is it's a 20,000-piece puzzle. Yeah. So anyway, if you're looking for a gag gift for your family, you could order it. That's on pranko.com. And it's actually only an empty box. There's no real puzzle inside. But on the outside, it looks like it's this 20,000-piece puzzle that's all blue with a little moon. And then when they open the box, it says, hi, you've been pranked, and you put your real gift inside. It's great. Anyway, but if you just have evil thoughts toward family members. But anyway, so I don't know if you ever did this, but you get down to, like, all the rest of the puzzle's done. It's just the sky, for instance, and you're like, I don't know how we're going to finish this. Every piece looks the same. We're like, that piece doesn't fit. This piece should fit there. Any of y'all, like, if the family wasn't watching, you kind of like fit the piece in and then take a hammer, bam, and make it fit? Y'all ever do anything like that? Yeah, you've done the hammer trick. It works great. It really does. It can make anything fit, you know? They're not lying when they say duct tape, WD-40, and a hammer. Those 3 tools can fix any of life's problems. Yeah, the hammer fixes the puzzle. Well, what we're going to do, we look at this and we're like, I have to take the square root of 3, but you can't do it. So we're going to take a hammer. We're going to make it fit, all right? We're going to make this work. I'm going to manipulate this until it becomes something I can take the square root of. 3 is no good. So I'm going to force it to become something it isn't. What's a number we can take the square root of, class? 9. I can take the square root of 9. Is there a way to force a 3 to become a 9? Sure. Multiply it by 3. And all of a sudden now, my denominator's not a 3 anymore, is it? It's a 9, and I can take the square root of that. I'm going to make it work. However, illustration aside, smashing the puzzle with the hammer only works once. Now, by the time you've resorted to pulling out a hammer, you've pretty much decided you're never making that puzzle again anyway, right? So you might as well use the hammer. But there's a right way and a wrong way to do things in life, right? Like, Pushing Brecken over the stairwell, wrong way to handle your differences, okay? Bible says to get things right with your brother and leave a gift at the altar or something like that. So anyway, the right way to do this is not to just multiply the bottom by 3. You know this from our chapter on fractions. What you do to the bottom, class, you got it to the top. So we're not technically just going to change the denominator. We're actually going to make a full equivalent fraction. Not 1/3, class, but 3/9. It's the same thing as a third. It just looks different. It now fits. It's now something I can work with. So now, like we saw a moment ago, I can take the square root of the denominator. What is the square root of the denominator now, class? 3. Can I take the square root of the numerator? Nope. But you know what? I don't care. Because this step only says I have to take the root of the denominator. So I don't care about the numerator. I don't care how ugly it looks as long as the denominator is good to go. And it is. So that's what we're going to do. We look at the example over on the sideboard. For your sake, Gavin, since you can't see it, we have the square root of 5/8. Well, you can't take the square root of 8, but see what you can take the square root of, class? 16. So what I did was I multiplied top and bottom both by 2 to turn 5/8 into 10/16. And I can't take the square root of 10, but I don't care. It's a numerator. I don't care about numerators. You ever feel like a numerator, Noah? Anyway, so we're going to leave the square root of 10, but I can take the square root of the denominator. I care about denominators. Hi, Brecken. I care about you. You're like a denominator to me. I care about you. Dad, you're always in the way. Just kidding. Just kidding. What is the square root of the denominator? 4. And so we get the square root of 10/4. And that's the example that we see over there on the side. Questions on that example for the second way of reducing radicals. We could, of course, do the same thing with cube roots. Write this down, if you would, the cube root of 3/2. Now, the thing is, you got to pay attention to the index, because on the surface, you might be like, oh, turn that 2 into a 4. Well, for a square root, sure, but that ain't a square root. That's a cube root. I can't take the cube root of 4. But I could take the cube root of 8. If I multiply top and bottom, Brecken, by 4. So now instead of 3/2, my fraction class becomes 12/8. And now I can take the cube root of the 8 to get 2. Can I take the cube root of the 12? No. But class, I don't care. It's a numerator. Leave the cube root of 12 for all I care. The important thing is the denominator is now rational. The important thing is that the radical now is just a whole number 12. It's not a fraction anymore. Does that make sense? Write one more down. The cube root of 2/9. Now again, if this were a square root, I'm in business. I take the square root of the 9, get 3. I'll leave the square root of 2 because I don't care and I'm done. But it's a cube root. So 9's no good. Noah? 27. Okay, so multiply top and bottom by 3 so that my radical now becomes the cube root of 6/27. And so what do I do now, Maddie? Now, I've had students ask, Mr. Desky, can you reduce the 6 divided by the 3, or the 10 and the 4 can reduce, or maybe the 12 and the 2? No. No, this is radical 6. This is non-radical, rational 3. The 2 don't mix. So no, leave it once you've got it there as the cube root of 6/3. Questions on what we're doing? Does it make sense? I've got a handout for you. It's in the description of the video, Gavin. And what I want you to do for now is just do the odd numbered problems from the handout. Do just the odd numbered problems on the handout. Just the odd problems on the handout. Probably need to work them on your own paper because, as you can see, there's not a whole lot of room to work directly on the handout. But figure out what number that denominator needs to be. If it's already good, wonderful. That's what we showed the first couple times. But if that denominator's no good, make it good. Take a hammer to it, make it work. all the odds on the handout. Check your first two, number 1 and number 3. We good on the first couple? Off to a good start. Excellent, keep working. Check numbers 5 and 7. Are we good to go on 5 and 7? You skipped one. Okay. Questions on these? I want to point something out. A lot of students will do this. Follow along with me for just a moment because we're going somewhere with this. Students won't see 12 times 3 is 36, even though that's super easy, right? Instead, they'll see 12 times 12, and they'll say, the square root of 60, 144ths. Now, you notice this is a lot bigger and uglier, right? I'm lazy, so I like to find the smallest possible number. But this way does technically work. It would give us the square root of 60 twelfths. However, there's another step that must be done to reduce it back down. You then have to recognize, well, 60 is 4 times 15, where I can take the square root of the 4 to get 2 times the square root of 15, old style reducing, over 12. And then you notice you could reduce down to get the 1 and 6. Technically, the same thing could have been done here. You might have multiplied by 8s to get 24 64ths, to get the square root of 24 over 8. But again, this now factors into 4 times 6, where the square root of the 4 is 2, and then you can reduce to get the 1 and 4 that way. Always look for the smallest number. Why multiply by 8 when you can multiply by 2? Why multiply by 12 when you could multiply by 3? Does that make sense? Continue working. There's an extra step at the end on number 9. So once you finish 9, check your answer. Starts off like all the others. Just multiply top and bottom by the 7, square root of 28 sevenths, but like the square root of 60, like the square root of 24, 28 could be factored down. So a little bit of a step there at the end. So we're not done with roots of factors. We're not done with reducing radicals part 1. The reason we had to teach that first is because it kind of bleeds into step 2 sometimes, or part 2 sometimes. And then this cube root of 4/5. What denominator do we want to turn a 5 into? Anyone? This is why you have to have your list memorized. What cube could 5 turn into? 125, 5 cubed, right? So I could turn it into a 125 by multiplying it by keep in mind, this is 5 cubed. Here I've got 5 to the first. How many 5s are missing? 2 of them, right? So that would have to be 25, wouldn't it? 5 times 25 would give me the 125. So I also have to multiply the 4 by 25. That'll give me 100 over 125. Take it from here, Breck, and finish it out for us. Right, now if that were a square root, I could do something with that, but the cube root of 100, there's not even any cubes in 100, so we're going to leave our answer just like that. Again, keep working on memorizing your squares and cubes and powers of 2 if you don't have them down yet. Questions on this? Are you going to do some of these for homework this evening? I want to take a look with you now at a new type of word problem that we're going to continue working on tomorrow. It's what I call a 2-digit number word problem. So next section in your notes, kind of an interlude in the middle of this work with reducing radicals, 2-digit number word problems. 2-digit number word problems. I call these 2-digit number word problems because these are word problems that are about 2-digit numbers. So being the creative person I am, 2-digit number word problems. Now, a 2-digit number is a number with 2 digits. For instance, 68. Now, there are 2 digits in 68. The first digit, class, is a 6, and the other digit is an 8. The value of that digit is 8. But the value of this digit is not 6. This isn't 6, 8, class. The value of this digit is 60. It is 6 tens. Does that make sense? That's what you learn when you learn place value. It's not worth 6, it's worth 60 because of the place it's sitting in. If the roles were reversed, now it would only be worth 6. But this digit would now be worth not 8, but 80. Whatever digit is right here is worth 10 times itself. As you work on the 2-digit number word problem, that next section in your notes, some things I want you to write down. First of all, I want you to write down that we are going to represent the tens digit with the letter T. T for tens. Now make sure you draw it in such a way it doesn't look like a plus sign, because that could really make things challenging for you. We're also going to have a units digit, which we're going to represent with the letter U. So the tens digit will be represented T, and the units digit represented U. But in most of these word problems, it'll reference the number, or the number itself. The number itself is always going to be worth 10 times the tens digit plus the value of the units digit, right? 68 is literally worth 60 plus 8. 86 is literally worth 80 plus 6, correct? So write this down. The number will be represented 10t plus u. 10 times the tens digit plus the value of the units digit. Let's look now at the word problem that's on the screen. And Maddie, if you'll read this for us nice and loud, please. Look at the first sentence. Each sentence is an equation in our system of equations as we continue using systems to solve. It says the sum of the digits. What are the digits? Well, the tens digit class is... No, the tens digit class is t. The actual digit of 68 is a 6 and an 8, right? Those are the actual digits. The value is not 6 and 8, but those are the digits. The tens digit class is simply t, and the units digit is simply u. So if it says that the sum of the digits is 5, that just means t plus u equals 5. Seems fairly straightforward, right? Questions? But then it says the number is. Do you see that? How do we represent the number, class? 10t plus u. So the number 10t plus u is or equals, well, what is the number? The number is what, Maddie? 9 more than 8 times the tens digit. Not the value of the tens digit, but just the tens digit. Maddie, how do you suppose I'd represent 9 more than 8 times the tens digit? 8t plus 9. And there's our system. If you will memorize these 3 facts, which I don't think are too hard to remember, 2-digit number word problems really won't be that hard for you. As long as you remember, class, that the tens digit is t, the units digit is u, and the number is 10t plus u. Of course, at this point, I need to get rid of the 8t, bring it over as a negative 8t class to get 2t. Positive u is equal to 9. Of course, we still have the t plus u equals 5. And now we're set to solve. Thoughts on what we might do now? Brecken? I could, or I could just change all the signs. Right? That would make the u drop out instead of the t. But if I changed all the signs, stay with me, that would allow the u to drop out. Take it from here, Brecken. And since t plus u equals 5, 4 plus what equals 5, Brecken? 4 plus 1. So apparently, Brecken, the tens digit is, and the units digit is 1. Class, if I told you I have a 2-digit number, and the tens digit is a 4 and the units digit is a 1, what would the number be? 41. Let's see if that's accurate. It said in the second sentence that the number is 9 more than 8 times the tens digit. What is 8 times the tens digit? 32. 9 more than that is 41. These are the types of word problems we'll be working over the next several days. However, it is not like the word problems that you'll be working for homework, though you will be using systems. Homework for this evening is to finish the handout. Do the even numbered problems on that handout that I gave you, the even numbered problems from the handout, and do 2 word problems that involve systems of equations, page 179, word problems 11 and 12. Page 179, word problems 11 and 12. We'll take a look at all of that tomorrow. Have a wonderful rest of your day. You are dismissed.